Hello everyone, my name is John, and today we'll be working on homework number 2, problem 2, which states that design a simpler circuit that implements the function fx1, x2, x3, which equals to the product of sum of m4, 6, and 7. Now the next part toward this problem is to draw a truth table, and we can create the number of rows here by using the formula 2 to the power of 3. We use 3 because there are 3 variables in the function, which equal to 8 rows. Now the first row of the truth table would evaluate to 0, the binary number 0, the next one would be binary number 1, and so on. Now since we're working with max term over here, with represented by the sign like this, we want the function to evaluate to false to 0. Since the number was 4, 6, and 7, starting from 0, 1, 2, 3, 4, when we reach M4, we would evaluate the function to 0. For M5 would be 1, M6 would be 7, and 0. We would get the equation of M4 by looking at the input and having them also evaluate to 0. For example, for X1 for M4, since it's equal to 1, we want the opposite. Because remember, we always wanted to evaluate to false, which is why we use the opposite sign right here. Then you do the same thing with the other inputs and with the other max terms. Now, whether we would use the POS or SOP form, we would decide based on how many numbers we have to work with. For POS form, we only have to work with 4, 6, and 7. For SOP form, it would be 0, 1, 2, 3, 5. In this case, we would use POS form because there are less numbers to work with. Now, to get the canonical POS form, we just take the original function, which is product of sum of 4, 6, and 7, and instead of 4, 6, and 7, we would use their input from x1, x2, and 3. Now, the next step after getting the form, we would use the Boolean algebra to simplify further the equation. As you can see, we use some theorem from Boolean algebra that can allow us to duplicate one of the parentheses, which equals to 4. Later then, on third step, we would be using the combining theorem to combine two parentheses, which is other. For example, the first parenthesis on third step will be evaluated to x, y, second parenthesis xy, 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 and xy. Now, with the combining theorem that states that the x plus y times x plus not y, which is equal to just x, we would use it to simplify further the equation, which you can see on the screen. Now, the simplified canonical POS form would be right here on the screen. Now, the next part toward this problem would be drawing the logic network. If you can see on the screen, I already have the formula right there, and we just use that. Since the plus sign in this case is represented by the or sign, or in this case, OR gate. And since there are two plus signs, we would use it to draw two OR gates with the input x1 plus 2 and x1 not plus x3. And if you look back to the equation right here, there's only two inputs that are being multiplied together. Since there's only one AND gate, we use this to draw an AND gate, which is represented by this right here, and there are two inputs. The overall output of this logic network would be the function. Now, to find the total cost of this logic network, we just have to find how many number of NOT gates being used, the OR gate and one AND gate. There are two NOT gates being used here, which is on x1 and x2, so we use the equation 2 times 2 equals 4. There are also two OR gates being used, and we get the total cost of 12. We use the formula 2 plus 2 times the number of inputs, and the number of inputs is 2, which equals to 12. Same with the AND gates, we use the same formula. Since there's only one input, we just do the original formula, and which equals to 6. Now, to get the total cost, we just add everything together from 4 plus 12 plus 6, which evaluates to 22. This would be the total cost of the logic network. Thank you for listening.